Hello. Today we're going to make a foldable for pH. We need to have a red, blue, and a green pencil and a sheet of regular unlined paper. We're going to start by folding the paper. We start with it upright, the holes on the left-hand side, and we're going to fold the paper from either side so that we have about a ½ inch gap in the middle so that we can put some numbers. After we fold our paper, what we're going to do is we're going to put the number 7 right here in the center in green or some color other than red and blue. After that, we're going to go on and fill in down at the bottom 0 through 6 in red and 8 through 14 in blue. Spread them out so that they fill the entire height of the paper. You may want to reserve a little space right up at the top to write pH at the top, right above 14, because that's what this scale is. It's the pH scale, which is the acid-base scale. Now, talking about the acid-base scale, I want to show you a little something. This right here represents pH, and it goes from 0 to 7, which is neutral. 0 through 7 is acid. And then above 7 up through 14 is basic. Right in the middle, neutral, we have hydrogen ions and we have hydroxide ions, which are in equal concentrations. You can see that the amount of red above the line and below, right here at this line, is the same. The reason for that is that water, which I've written as HOH up here, even though it's a covalent compound, a very, very small amount of water does actually split into an H and an OH. Now, if it splits into an H and an OH, it makes sense that the number of H's and the number of OH's is exactly the same. So it's no more acidic than it is basic. It's got the same number of both. Now, as we move over to the left side, the number of H's increases. This is because we have added an acid of some kind. Now, an acid, which I have represented up here as HA, dissociates into an H ion, a hydrogen ion, and some generic anion, whatever that happens to be. And as we add H, the amount of H increases. You can see the red here is getting larger. The amount of OH decreases. And you might wonder about that if it's produced by the water. The reason for that goes back to what water is made of. Water is made of H and OH. And as I add more H's, due to the acid, they consume the OH, and we know that H and OH together go back to making water. So as we add more H, in addition to having more H, we have less OH because it's consumed and turned into water. Now, on the other side of the line of neutrality here, we have basicity, how basic is a solution. And that goes from 7 up through 14. As we move to the right, we're adding more and more OH, and we have less and less H. The OH comes from a base. This is a generic base. It's a metal hydroxide, like sodium hydroxide. Sodium is the metal, and the hydroxide here is what makes a solution basic. It dissociates into a metal and the OH. As we add more and more of the OH into the solution, the OH increases, and the H disappears for the same reason that the OH disappeared in the acid. That's because, of course, water is made of H and OH, and as we add more OH, it combines with the H's and consumes them and turns it back into water. So by the time we get to pH 14, we're all OH and almost no H left. How much, I'll show you in a later slide. Now, we're going to make our foldable with some text here next to the numbers, and then we're going to draw 5 pictures on the inside flap. Don't write this down now. We're going to look at this inside flap where I'm pointing first, and we're going to have 5 pictures. So this will be the inside flap, and the first picture will go down at the bottom. As you can see down here, I have 4 H's in solution. So in a very low pH, pH 0 or 1, we are almost entirely H's, all H's. You don't see any OH's here. As we move up to the next slide, you can see there's 1 OH in here and all the rest are H's. So it's mostly H and a little bit of OH. When we get to a neutral solution, we have 1H, 1 OH, 1H, 1 OH. So we have an equal number. The number is equal for OH and H. You can see the trend developing here. As we move up one more, we are mostly OH and only 1H here. And as we get all the way to the top, we're now mostly OHs, or all OHs. So this would be up around the 13 or 14 region of the pH scale. Now let's look between the numbers and this inside flap and see what we're going to fill in on the text. You can see the pictures here we've drawn, and we're going to label the pictures. So at the bottom, this is all H. As we go up, we have more H than OH, or more H, less OH. Right here, we just noticed that for pH 7, H and OH are equal. Go up a little higher, we have more OH and less H. And finally up at the top, we're to all OH. So this is a very, very basic solution. Just like the bottom is very, very acidic. Now we're going to close up our foldable, and we're going to write up in the upper part H in square brackets, H plus ion, and hydroxide, OH minus, in square brackets. The square brackets have a meaning, and we've discussed it before, but the square brackets, when read aloud, essentially mean the concentration of. So when I have H plus inside, I'm saying the concentration of hydrogen ion. And over here, I have the hydroxide ion, so I would read this as the concentration of hydroxide, or hydroxide ion. We're going to fill in some numbers now. We're going to write 1 times 10 to the negative 7 right next to the pH of 7. This is the hydrogen ion concentration. And you remember that we learned molarity. So this is 1 times 10 to the negative 7 moles per liter, or 1 times 10 to the 7 molar concentration of hydrogen ions. You may think that the 7 here, the negative 7 and the 7 are a coincidence, but they're not. Let's fill in the rest of the concentrations. As you can see, as I move down the line of acidity towards 0, the concentration becomes higher and higher. 1 times 10 to the negative 1, that's 0.1. Whereas this up here, 7 is 0.00000001, so it's a very small number. If you see the trend here, you can imagine what the next one is, and that is 1. 1 times 10 to the 0 is 1. Anything raised to the 0 power is 1. Some people think it's 0, but it's not. Well, now that you know the trend, it should be pretty simple to fill in the top. The top part just goes up like this, all the way up to 1 times 10 to the negative 14. When you're done with that, we're going to move over to the other side. On the other side, we're going to also write 1 times 10 to the negative 7. But wait, we're not going to fill in the numbers the same way we did on the other side. We need to fill in the numbers, but notice they are backwards from the way they appeared on the left side or on the right side. If you look, you'll see there's still a pattern. This number right here is 0, but look here, this negative 1. If I forget about the sign, 1 plus 13 is 14. 2 plus 12 is 14. 3 plus 11 is 14. 4 plus 10 is, you guessed it, 14. So there is a pattern here. Let's go on and continue the pattern all the way down to the bottom. And you can see that it's the same pattern as on the other side. It's just completely reversed. So when you're finished with that, let's take a look and see what we understand from these numbers. Now, if you're not used to looking at numbers in scientific notation, it may be a little less confusing if we show you what these numbers look like in regular decimal form. You can see that 1 times 10 to the negative 14 is a very, very small number. So at pH 14, the hydrogen ion concentration is so low that we can basically say there's none of it left. As the pH goes down towards an acid, a stronger acid, here of course it's a base, here it's neutral, but as we get further and further down the scale, we end up with 1. That means a 1 molar concentration of hydrogen ions. With a strong acid, 1 molar hydrochloric acid, for instance, we would have 1 mole of hydrogen ions per liter, and that would give us the pH of 0, the lowest on our scale. Now what about if 1 molar solution of HCl gives us a pH of 0, what if I had a 2 molar or a 5 molar? Could I keep going? Yes, you could actually do that, and if you did, you would have a negative pH. Now it's not going to go much further than -1, -1.5, because at that point we can't add any more hydrochloric acid. Hydrochloric acid has a limit of several molar, but we can't keep going forever. So we can have a negative number, and we can also have a number greater than 14 for a base that's very basic. But this pH scale is designed around a 1 molar solution. So really it doesn't have much meaning if we have a concentration that's higher than 1 molar. And what do these numbers look like on the other side? Well, of course, they look exactly the opposite. So here's a question for you. Do these numbers look kind of familiar? What about the shape of the numbers? The shape of the numbers should be familiar to you. Let's try it now with a whole bunch of insignificant zeros added on. And notice the lines of the ones through the center. Let's draw one of them. If I could overlap these, we could see a little bit better. How about now? Move this to the center so we can look at it, and what would happen if I did this? Look a little more familiar? How about this? Starting to look a little more familiar now? What do you think? It should be familiar now. This is our high concentration of acid, 1 molar, and it goes all the way down to 1 molar of hydrogen ions, all the way down to 1 times 10 to the negative 14 molar of hydrogen ions on this side. Now, if I had overlapped the numbers, you would see that as we go this direction, we go up to 1 molar of OH. Now let's continue with our foldable, and we're going to look at the inside flap, and we're going to talk about strong and weak. Before we do that, let's talk a little bit about electrolytes. This is a review from what you already know. An electrolyte is something that splits into positive and negative ions, and therefore, since it has mobile ions, mobile charges, it can conduct electricity. This is an example of a non-electrolyte. You can see that there are positively charged particles or cations and negatively charged particles, anions, but in every case, in all 10 of these, the cation and the anion are connected. They're essentially small molecules bonded together, and they don't separate. So the solution or the solute in the solution is not ionized, so it's a non-electrolyte. We learned about weak electrolytes. I have the same 10 particles of material in here. They could be a salt or an acid or a base. But only 2 of the cations are free and 2 of the anions are free. The other 8 are still bonded. So essentially 20% in this drawing here has been ionized and the other 80% is not. This is considered a weak electrolyte, even though it's the same concentration as the non-electrolyte here. A strong electrolyte, this is the same concentration. A strong electrolyte is completely ionized, 100%. So there are no bondings between the cation and the anion other than the occasional random bumping into each other that occurs in a solution. These are completely ionized. These are free to move. So a strong electrolyte, of course, conducts electricity much better than a weak electrolyte because it has more charged particles in solution. So what does this look like with an acid? In this case down here, I have a weak acid that is dilute. There are 5 particles of acid in this box. 4 of the particles of acid, represented by H and A, are not ionized. They're stuck together. Only 1 of the 5 has split into a separate hydrogen ion and a negative anion. So essentially 1 in 5, so about 20%. With a strong electrolyte, I have the same 5, but it's 100% ionized. So of those 5, all 5 have split into separate hydrogen ions and anions. What happens if I take this weak acid and I add more of it? Do I make it more acidic? The answer is yes, but not necessarily a whole lot more acidic. Here I've gone up to 10 particles in this box, and you can see that only 3 of them in this case, that'd be 30%, are ionized, and the other 7 have remained together as HA. So we still have only partial ionization of this weak acid. Is it more acidic? Yes, because there are more H's. But that's because we've increased the concentration, not because we've increased how much is actually ionizing and splitting apart. As a matter of fact, in this case, which I made up, it is still a weaker acid, or I should say less acidic than a dilute solution of a strong acid, because we only have 3 H's up here and we've got 5 down here. And it's entirely due to being 100% ionized here as opposed to only 20 or 30% here. Now on to a strong acid, which is concentrated. Here I've got the same 10 particles that I have here, but all 10 have ionized. So this is considered a strong acid. Notice that down here, this is not a weak acid. This is still a strong acid. It's just dilute. So we don't refer to strong and weak when we're talking about the concentration. We talk about strong and weak this direction when we're talking about the percentage of ionization. Okay, so this is weak dilute, weak concentrated. This is strong dilute. This is strong concentrated. So we're going to write this down on the inside of our foldable. We're going to go on the left inside flap, and we will draw a picture down at the bottom. We're going to have a total of 4 pictures. The first one will be our strong acid, completely ionized. So the little black circles are our hydrogens, and the blue circles are the anion, whatever that may be. It could be hydrochloric acid, so then we have H's, and these big blue circles would be chlorides. And we'll write in a description right here, a strong acid, completely ionized. The next picture up, which will go up through up to about the halfway point will be a weak acid. It's only partly ionized in this case. So I have the same 10 circles here, but you can see that 8 of them are still held together. They have not ionized. And only 2 of them, there's one and there's the other, and there's the anion and there's the other anion. Only 2 of them have ionized. Now this is exaggerated. It's only 20% ionized, but technically speaking, anything that is not 100% is considered a weak acid. So strong acids are 100%, and weak acids are anything less than 100%. Now let's move up to a base. In this case, I've gone back to the MOH representation of a base, a metal hydroxide, like sodium hydroxide. Now this one here is not sodium hydroxide. This is a weak base. I've got 4 base particles here in this little beaker, and 3 of them have not ionized. 3 of them are still together. This one, and this one. Only one of them has split apart into the metal cation and the hydroxide, which is what makes it basic. So this is a weak base, and we'll describe it as a weak base and then parenthetically partly ionized. The last one is, of course, a strong base. I have the same 4 particles, but they are all ionized. So there's a lot of OHs in here. Remember, we added the same amount in the weak base and the strong base. They both have the same number of particles. But which one has more OHs? Well, it's the strong base because of the 100% ionization. So this completes the foldable on the front side. On the back side, we're going to do some measurements of household chemicals. We're going to look at lemon juice, we're going to look at ammonia, and a few others, and we're going to test them with litmus paper, which is the most common method for testing acids and bases. Litmus paper turns red in the presence of acids, which is why we use the color red for our acids. And it turns blue in the presence of bases, which is why we used blue for a base. Now it doesn't turn green for neutral. In reality, when we test with litmus paper, we always test with both, because a neutral solution won't change the color of the litmus paper. So if I test a solution with blue litmus paper, it could be a base because it's blue, or it could be neutral, in which case it's just wet blue litmus paper. So in order to make sure that it is really turning blue, I test it with red litmus paper and see if it changes to blue. So I always test with both colors, and if they stay the same, it means it's neutral. And if they both turn to one color, either red or to blue, then I know that it's either an acid or a base. So save this paper, and tomorrow we're going to be writing on the back and doing some testing. In addition to litmus paper, we're going to test with universal indicator, we're going to test with phenolphthalein solution, and we're going to test with some pH paper strips.